Hi there, this is David A. Wheeler, and this is a little screencast on creating functions in metamath. Here's my outline. We're going to be creating functions, well, one function at least, in metamath. If you don't know what that is, go to us.metamath.org, and it's metamath proof explorer, that's set.mm. We're going to use signum, aka SGN, as our trivial function, as an example. And we're going to modify set.mm. First of all, we're going to tell it how to typeset it, the $T section. Then we're going to define a constant for SGN, indicates a class, define it, verify its proof and markup, and then prove its function application in at least one value. We need to tell metamath how to render the function. It might have a very interesting display. In this case, SGN will just be displayed as SGN. So in the $T, the typesetting section, we'll just say that the definition, the HTML definition is just SGN. For alt HTML, the Unicode version, it's SGN. For LaTeX, it's SGN. We now need to actually define it. I should note that I'm just using an ordinary text editor. I happen to be using Vim, which has some syntax highlighting, but you can edit with any text editor. So first of all, we're going to say that there's a constant called SGN, or signum. Extend the class notation to include it, and then actually define it with a preceding comment that explains a little bit more about it. You'll notice that by convention, the label for defining a function is just df dash and the name of the function. It's a $A because we're defining something. We're saying that SGN is a function where x is a member of RR star, and it maps that value to this expression to the right, which simply says if x is 0, it's 0. If it's less than 0, it's -1. Otherwise, it's 1. You'll notice that x has to be a member of RR star. That's a decision I made. RR star is the reals, also including plus and minus infinity. I've decided that SGN would be useful to apply to plus and minus infinity. This is all well and good, but let's make sure that it's actually correct. We're going to verify both the proof and the markup. Doesn't take long, and I prefer just to check everything. As I said, it doesn't really take that long. That way we can be sure that a whole bunch of problems are prevented. We've defined a mapping, but usually you apply a function directly using a function application. In set.mm, that's the backquote operation. So we need to prove that function application is what we think it would be based on the mapping. No big deal. Usually these are called function name val. I'm going to define it as an alternate because I actually already have this defined. And we're going to prove from the mapping that indeed the function application does what we would think it would do. So first we're going to prove that, hey, if something is a member of the reals, if some class A is a member of the real of the RR stars, then applying that function does what, well, you would think it would do. All right, so here's what we need to prove. How do we get started? Well, all too often when we're doing some mapping and we're trying to find out what the actual function application is, we're almost certainly going to start out with some variation of FVMPT. You can see this by looking at a lot of the other times when people do this. So I've typed that in, typed in Control-U, and there are some preconditions, some hypotheses I need to fill in. Basically, in particular, the second one here is it needs to know what the definition of the function is. I need to be able to prove all sorts of things, but let's start with, well, I already know what the name of that one is, right? That's df-SGN. I'm going to put Control-U again. Now we have more information. It says, hey, if something is a member of the reals, then here's this definition. Now I already know that that has to be some set variable, so I'm going to arbitrarily pick x. Doesn't matter. We're just going to be consistent about it. I typed in Control-U, and now a whole lot of stuff has been filled in. This is going to be proved if D1, D2, D3 are, if I can prove each of those things. D3 says, hey, can you prove that this is going to produce something in the sets, basically in underscore V. Not going to worry about that right yet. This one we've defined. We just pulled in from the definition. So now what we need to do is show that if some x, so basically we need to show that we can apply an arbitrary class, not just a set variable. That shouldn't be too bad. Let's look up here. If x is an a equal to a, then applying it to x should be the same thing as applying it to a. That doesn't seem like that would be terribly difficult to prove, right? Well, let's see. If you do some searches, and I'm not going to bore you with those here, we're going to go back. You'll find that because these second parameters are identical, there is a step we can use to prove this. And that's going to be IFBI EQ second. Type in Control U. Alrighty. That works. What do we have to do to make that work? Well, equal, equal. And in fact, we can already prove that. So now we're back to if x is an a, then these two things need to be equal. And you'll notice that, for example, these second parameters are the same. These third parameters. So let's go back a little bit further. And basically, if these two are the same, and these two are the same, then we're fine. That's really just going to be IFBID if you look that up again. Excellent. We've proved the first and the second parts of this. Now, that all looks great. We're going to need to fill in this last piece. Well, how can we do that? Well, this last one says basically you need to prove that the resulting of all these if expressions is going to be a member of underscore v's. Well, it looks like it's all built up from things that are members of sets, right? So let's kind of think forward a little bit. I find it easier to think forward this way. So let's look at this for just a second. So I need to be able to prove that this whole expression is going to become a member of underscore v. Well, let's see. I find, as I said, let's start with the first principles. So I'm going to say, hey, you know what? I know that 0 is a member of underscore v, right? Let's type that in and see if it can find that. Nah, I can't find that. Well, drat. But I know that 0 is a member of the complex numbers, and it knows that too. Well, if I can prove that, I can easily prove from that 0 is a member of v, right? Absolutely. Well, if we can manage to prove that for 0, we're going to need to prove this for 1, right? And minus 1. Let's try this again. Is minus 1 a member of underscore v? Oh, it's got that one. Let's try again. How about we're going to need to prove that 1 is a member of v. No, it doesn't have that, but it does know that we got complex numbers. Excellent. So let's, based on the previous value, we can now prove that 1 exists in underscore v, right? Yeah, there we go. Now I think that we've got more than enough information to prove to get a little more complex here. What we really want to start proving is that this portion of it's going to be a member of underscore v. Let's do that. All right. Okay, is that going to be a member of? Well, it's going to need some information. There's two possible cases. It can reproduce a minus 1 or a 1. And let's see here. We know that minus 1 is a member of v, and we know that 1's a member of v. Let's do Control U. It found that now. So let's do. Now what we really want to do is find out that this whole expression, we've now proven that the right-hand side is a member of v, but if can produce either a 0 or a, well, in that case, we already know it can produce the right hand, that's 400. We also know it can prove the left hand, that's 100. Okay. Well, that didn't work. Oh, of course, I'm referring to the wrong label. This one says that 0 is a member of the CCs, which is true enough, but we want to know that's a member of V. Now let's try Control U, and it's proven. And we can copy and paste this into the actual set.mm, and we have now proven that SGN val really is what we thought it was. It's important to define some specific values that are pre-calculated. For one thing, a lot of proofs often end up using some specific values, and I also find it useful to gain confidence that the definition you gave is the one you intended. So let's define what signum of 0 is. Hopefully, we should be able to prove that the signum of 0 is 0. Well, one thing we know we're going to need is the definition of signum when it's applied as a function. So that by convention, that's always the name of the function with val. Let's do Control U. And oh look, it's loaded up the definition for us. Well, in this case, we don't want an arbitrary definition. We want to know the definition when we apply it to 0. So let's apply that, Control U again, and it says, hey, if 0 is a member of RR stars, then signum of 0 is equal to that, and then we're going to need to prove that that whole thing eventually simplifies down to 0. Before we even go very farther, let's admit, though, that we should be able to prove that 0 is a member of the RR stars. What do you think? Let's see here. Yep, that's already a known fact in the database. So let's simplify this down. 120, if we depend on that and that, we should be able to prove within the turnstile that, okay, that basically we're able to, those two are equal. Control U. Uh-oh, we have an error. Oh my goodness, can't have one of those. Oh, extra paren. There we go. Alrighty, so by modus ponens, we have simplified it down already. Now we just know that if we can prove that signum is that, if we can prove that this is, we already can prove that this is equal to that. If we can prove that that equals 0, we'll be okay. Well, how can we do? Well, wait a minute. If 0 equals 0, then it's 0. Well, now let's see. I'll bet we can prove that 0 is 0. What do you think? Okay. In fact, this is going to be just, things are always equal to themselves, so that is hardly a challenging thing to prove. Now, if we take those two things, we should be able to ask questions about, in fact, let's see here. Well, let's pull this out. Alright, we should be able to prove that if 0 equals 0, right, that implies that this is an overly complicated way to do things. Really what I know I need to do mentally is there's already something in the database that lets me tell you if something is true, then we can pull out the first part. So here's my if expression here. Okay. We can just substitute that in right here. Now Control U. See, if 0 equals 0, then that whole expression simplifies down to 0. Excellent. Well, since we know that 0 equals 0, and the 0, 0 implies that we should be able to do this, 320 based on 200 and 300, we should be able to determine that this whole thing is the same thing as 0. Oh, we forgot our turnstile. There we go, another modus ponens here. So, let's see, we have managed to prove that this lengthy if expression is equal to 0. Oh, but wait, that F expression up there is, we've proved earlier, is the same thing as signum. So if we combine 120 with 320 and do Control U, we have now proven it.